Hello, everyone, and thank you for joining us for today's webinar, Design Sensitivity and Optimization with Simcenter Nastran and Femap. My name is Jonathan Hill, and today I'm joined by my colleague, Anthony Riccardi. And normally we'd both be calling in to you from ATA's Northern Virginia office right outside Washington, D.C. Before I turn things over to him for our main content for today, I'd like to give just a very brief intro and overview of ATA for those of you who might not be familiar with us. ATA is well known as a provider of high-value engineering services where we have expertise in design, analysis, and test. We get really excited every day to help our customers overcome their most difficult product design challenges across a wide range of industries, just some of which are shown here. We're also able to leverage that experience and expertise through our role as a Siemens partner and value-added reseller. In that capacity, we offer training, free resources, and hotline support for a variety of products, including Simcenter Femap and Simcenter Nastran, which we'll be discussing in greater detail today, but also other really great tools like Simcenter 3D, NXCAD, and Star CCM+. We host a technical support hotline, which is available from the beginning of the day on the East Coast until the end of the day on the West Coast, and that can be reached by both phone and through our software website. And I also always like to point out that we actually develop and are the preferred North American provider of Simcenter Nastran training materials. In addition, I'd invite you to check out our software website for a lot of great content after today's presentation. I always like to highlight these free resources because there's a lot of really great content up there. It ranges from white papers and APIs to other presentations and on-demand webinars. The best part of all this, I think, is that we really tailor this content to what we hear from the users that we're talking to. So my final request would be that if you have ideas for future webinars or other resource topics that you'd like us to consider, definitely feel free to reach out to me and reach out to us, and we'll see if we can make that work. With that, though, I'd like to go ahead and hand things over to Anthony for our main presentation.
Thanks, Jonathan. Thanks, everybody, for joining us. So before we get into it, just checking participants here. Wow, looks like we got a lot of people. It's really great to see everyone. So there's a lot to cover today. The target audience for this, which I expect you're a member of, is really focused on two groups: those that are experienced with Nastran and maybe new to optimization or just want to get a refresher on it, and then also those that are experienced with legacy Nastran and optimization, but maybe new to the more recent developments in the past few years. Topology optimization was added to Simcenter Nastran, which is the new name of NX Nastran. So starting at NX Nastran 12, topology optimization was added as a new feature. And then in Femap, the optimization support was redone starting around the same time to add topology optimization support and also completely redo and enhance the design optimization support. So it's much more capable now. So I'd encourage anyone, if you're using Femap for optimization, get the newest version, but at least try to get to version 12. That's going to make a big difference for you. So we'll be using the newest version of Femap for the examples today. It'll be similar interface to what it was starting with Femap 12. The objectives are going to be introduce and review the fundamentals of design sensitivity and optimization, introduce you to the Nastran and Femap capabilities, and then demonstrate Nastran and Femap to reinforce this understanding and help you get started. I can't cover everything. This is a short webinar for the type of material that this is. It's a rich topic, and so I can help you get started in this time, and I'm going to do my best to do that. So the outline falls right out of those. We'll cover fundamentals. We'll cover the specific capabilities in Simcenter Nastran and Femap, and then we'll get into some live demonstration examples, sizing a beam cross section. We're going to look at this from an analytic solution using hand calculations. We'll look at the graphical picture of the design space and be able to see what's our feasible region, where our constraints are limiting our feasible region, visualize the objective function and really see the design space and see the solution, have a good fundamental understanding for a simple problem, and then we'll demonstrate that very same problem using Femap and Simcenter Nastran from scratch. I'll build, it's a very simple model. I'll just build it really quickly. We'll go through the entire process. You can, if you want to watch the video later, follow along with me and recreate the same solution, you can do that. Topology optimization example will be the second one. We'll, again, I'll build it from scratch. It'll be a simple model. It's going to be inspired by a Sigmund paper where he presented his 99-line topology optimization code. So I'll share a reference on that you can go explore on your own time. But there's a specific example in that we'll reproduce using Nastran. And then the last example will be a bigger problem with a larger aircraft wing structure. We'll just look directly at the Femap and Nastran solution. It's going to have many design variables, multiple subcase types to show you, a demonstration with some of the more realistic problems that may help you understand how to apply this to your design challenges. I'm going to try and finish this within the time that we have. We may stop for questions some point in between the second and third example. If I feel like I want to give people the opportunity to ask questions, you may have a meeting after this before we finish up, or we may be able to finish in time. So we'll see how that goes. Design sensitivity and optimization. What they are is sensitivity analysis is computing a rate of change of a structural response with respect to a change in design variable. In calculus, you call this a derivative or a gradient. In design optimization, sometimes you call it a design sensitivity. It's a derivative. You take the derivative of the response with respect to some design variable. So that could be a plate thickness, it could be a beam cross-section dimension. You can take the derivative of the response, say for a bridge, how's the span, deflection, what's the derivative of the deflection with respect to the member thickness? You can calculate that. In automotive design, you may want to calculate a resonant frequency and how the frequency changes with respect to some panel thickness. So it's a derivative of the frequency with respect to the panel thickness. So you can calculate that, and it's useful for a few different things we'll discuss in the next slide. Design optimization is an automated process. It uses an optimizer to generate an improved design. So it implements a formal algorithm to search for the best design. Gradient-based optimization algorithms use design sensitivities to guide the search process. And those are the types of algorithms used in Nastran. It uses gradient-based optimization algorithms. It's calculating sensitivities to implement those algorithms to help you achieve a better design. So sensitivity analysis on its own, it can be useful for just understanding the derivatives that you may be interested in, to understand how the responses are changing with respect to your adjustable parameters. It can be used to create approximate or reduced order models that use sensitivities, which you may then go on and help you rapidly investigate uncertainty quantification. And then also gradient-based optimizers use sensitivities. Optimization itself, you can use an optimizer to help you produce the best design that satisfies your requirements. You can compare completely different configurations. The fair way to do that, if you want to compare, say, a suspension bridge to a truss bridge, would be to optimize both configurations and then compare them for a fair comparison. So that would be a trade-off feasibility study. And then you can also, another example would be updating models to correlate with test data. If you have a modal test, you may have modal parameters like modal frequency that you want your model to match, and you may have uncertainties in your model that you know about, say the joint stiffnesses, where you want to update those values to get a better correlation with your test data. So you can use Optimizer to do that. That's a few examples. So when you think about this in the context of engineering, what we're looking at in engineering is we have a physical system and a design problem. So it's either a physical system that exists in real life or a design that will exist in reality once it's built. So for example, a flat plate with a hole in it that's loaded. The design problem for that application could be sizing that hole radius to minimize the weight of the plate, but not exceeding the allowable stress. So in typical analysis, you would create a mathematical idealization of the physical system. So this could be a finite element mesh. So here you see the example for the flat plate with a hole in it. There's a mesh. There's some boundary conditions that are taking advantage of symmetry. The loads are applied, and you can use this analysis model to predict the response. So in this case, we want to look at stress and make sure we're not exceeding the allowable stress. For optimization, we need to parameterize this mesh by the design variable itself. So this is actually one of the more complicated types of optimization for the specific example where, changing the radius of this hole, we'd actually have to morph the mesh such that it's parameterized to adjust with the whole radius changing. So you would have to set that up. And then in addition, you have to specify your design model, your formal statement of the design objective, your design variables, and your constraints, which in this case, you want to minimize weight, you want the stress not to exceed the allowable, and the design variable is the radius of the hole. So the basic problem statement that our optimizer is going to solve, the basic problem is it's going to minimize an objective function. It's going to do that by varying design variables that are related to our model that update the physical model. And those changes are going to be subject to some constraints. So like an inequality constraint could be a stress constraint. The stress has to be under some allowable. An equality constraint would be something like the modal frequency has to match the test modal frequency. And bounds are bounds that we know ahead of time where we know the limits of our design variables. It's not a function of the system response, but it's just something that we know ahead of time, say like that the radius of that hole has to be a positive value. So the lower bound would be some small finite value because a negative hole radius, it doesn't make sense. So that's the problem statement. And this basic problem, we can solve this using Nastran. So the same way we have inputs that describe our analysis model, our mesh, our loads, our boundary conditions, our cases, that same type of information we can specify our objective function, our design variables, our constraints. There's Nastran input data that allows us to describe this problem. And then we can use Nastran and Nastran's optimizer to solve design optimization problems. So that's what this is about. Femap and Simcenter 3D are preprocessor tools that support optimization preprocessing. So the same way where you use Femap to set up your mesh, you can write your input file. You can include optimization inputs, and Femap will create those for you. Or Simcenter 3D, which is another software tool that we use at ATA, you can create those for you. So this is a capability that you can use. A very high level explanation of the design optimization procedure that Nastran is going through is you provide your initial model, your initial design. Nastran runs the analysis, evaluates it for a specific set of design variable values, evaluates the design objective and constraints for that specific design, evaluates the sensitivity of the critical responses for that design, and then creates uses an optimization procedure to update the model. And as part of that procedure, it creates an approximate model based on the sensitivities and a gradient-based optimization algorithm to explore the region of the design near where that approximate model was created to update the model. And then that process iterates until the convergence criteria is satisfied, and then you get a final design. So it rapidly updates. You can explore the design space efficiently and in an automated way using Solution 200 in Simcenter Nastran. So that's the 10,000-foot view of the process. Some specifics in terms of just the Nastran inputs and Nastran capabilities. You're using the same input file that you'd be used to. There's an executive control section where you'd specify like solution 101 for static, solution 103 for normal modes. For optimization, it's solution 200. And then the specific analysis type, you select in the case control section. And there's bulk data inputs that you define in the bulk data section for design variables and relationships and responses. So I'll go into a little bit more detail on the following slides for that. there's a lot of, there's going to be a lot of material on these slides, and I'm not going to cover all of it. The main point I'm trying to get across here is these are the capabilities that are available to you. And so in terms of optimization analysis disciplines, those are sort of categorized in terms of the analysis types that you're used to: statics, modes, buckling. The types that are listed in this table are the types that you have access to for design optimization. There's a subset that are available for topology optimization, and a subset have native Femap support, meaning user interface only with no direct text modification. They're shown there. It's controlled in the case control section using the analysis command. And you can run more than one subcase in a single optimization run. So this is a little bit different than normal analysis where you will have a statics run and a separate modes run. Because you want to consider multiple disciplines simultaneously, potentially, you can run them in the same run. So the different subcases can have different analysis types, and the ones you can use are listed here. In the bulk data section, you're going to find design variables. There's these entries I'm listing in a monospace font. I'm not going to read all those to you, but I just want to make you aware of the capabilities you have. So you define design variables and bounds, optionally define discrete variable values. You can optionally use design variable linking, and then you can relate those design variables to your model itself. So relate design variables to connectivity information, material properties, element properties. There's linear variable to property relationship support sort of automatically, but you can also use an equation to arbitrarily define relationships. There's entries that allow you to do shape optimizations, to morph your mesh or move nodes. And then there's entries that allow you to automatically create thickness design variables and then to create design variables for topology optimization. So again, yeah, I'm just covering some of the highlights here. There's data, there's these bulk entry data names that I'm not going to read through here. I have, we offer classes where we go through in more details all different entry types, but here I'm trying to convey the capabilities that you have by showing these entries. So specifically for design response quantities, there are many response types. The ones that you would think of obviously would be stress, modal frequencies, displacements. There's many listed there. That you can access using the design response one entry. You can also create arbitrary equations to create more complicated functions of those more basic responses, or even evaluate responses externally. But the way that works is you create the design response, and then you also, in the case control, specify which response is your objective function, there's entries that you define constraints, and then in the case control, you say, these are my constraints for whatever subcase the constraint is active in, and those can be subcase specific. There's also topology optimization specific entries. The DVT rel 1 entry automatically creates design variables for topology optimization. So you create a group of elements that you want to optimize using topology optimization. It automatically creates design variables for those and links the material properties to the design variables using design material relationship law. There's a default material law. You can control that if it's useful in your situation to fine tune the way that the topology optimizer is adjusting the material properties to achieve the topology optimized design. And there's also topology optimization specific design constraints. Specific design sensitivity, you can output the design sensitivities. You can control that using those two entries that are listed there. There's a case control command and a bulk data parameter entry that allow you to actually output the design sensitivities. There's various formats. You can get text format, binary formats of different types. You have to look that up and pick the one you want. You can request sensitivities only, so you can completely skip optimization and just have Nastran calculate the sensitivities. You still need to set up the design variables and responses like an optimization problem. And for that, the general recommendation would be define a violated constraint for each response quantity that you want sensitivities for. And it's important that it's violated because there's some screening that Nastran does to reduce the sensitivity computation cost if constraints are not violated, then they may not, the sensitivities may not be calculated. So you define a violated constraint for each response quantity, and then you can create a dummy objective function like weight would be a way to get the output that you want and skip the actual optimization if all you're interested in is the sensitivity output. Okay. I'm going to get to a live optimization interface walkthrough. I'll wait till we get to the example to do that, but I'm going to show how to set up these problems in Femap, and at that point, we'll look at the interface. But we'll do that as part of this first example. So this first example is a beam sizing optimization problem. We see on the far left, we have a beam. It's 5 meters long. There's elastic modulus and Poisson's ratio defined. Length is defined, but we wanted to optimize the cross section, this base and height of the beam cross section. We're going to load it in 2 loading conditions. So a 5,000 Newton vertical load, a 100 Newton horizontal load. And we want to minimize the volume of this beam, which is the same thing as minimizing weight for uniform density structure. The design variables are the cross-section dimensions. We're going to apply constraints on stress. So the stress due to bending and the displacement due to bending are going to be limited to 200 megapascals and 10 centimeters. And we have bounds on our design variables, so it's going to vary from 1 to 30 centimeters and 1 to 5 centimeters for the 2 dimensions. So we're going to solve this problem 2 ways. We're going to start with, hand calculations based on beam theory. So the critical stress that we want to limit for this beam is going to be along the root, and the top and bottom edge are going to have equal and opposite stress. That's going to be the maximum. From beam theory, we can use the relationship of stress relating to the moment and the stress location and moment of inertia to calculate the stress by hand. So you're probably familiar with the term, bending stress is moment times the distance from the neutral axis divided by the moment of inertia about the neutral axis. So what we want to do to handle this for our optimization cases, we want to write this stress in terms of our known quantities and our design variables. So the moment is this load times the length of the beam is going to be the moment at the root. The distance from the neutral axis is going to be half of the height if we're looking at a stress point along the top edge. The moment of inertia for this cross section is 112 base times height. And so we plug those values in and simplify, and then what we have is a stress as a function of known quantities and the design variables. So that's exactly what we need. For the tip displacement, we will use beam theory again. There's Euler-Bernoulli beam theory differential equations we can solve to calculate the tip displacement for these specific boundary conditions. For simple cases like this, you can look up reference solutions in a textbook typically, and you'll find the solution for this specific case is equal to this equation shown here, load times length cubed divided by 3EI. And the same thing goes here. We want to write that moment of inertia since it's a function of our design variables in terms of the design variables, substitute, and then we have tip displacement as a function of our design variables and known quantities. So this is for loading case A. If you remember, there's a horizontal loading case. It's analogous. I'm not going to derive that whole case, but essentially what happens is you flip B and H in these equations because the load is in the other direction. So you can rederive that if you're interested, but it's the same process. So to apply this hand calculated solution graphically to our design space, the last thing we need is our objective function, which is volume. So that's length times base times height. It's geometric result there, and now we have everything we need. So we can, since we only have 2 design variables, we can plot our design space on a 2-dimensional plot. So we have our lower and upper bounds on beam width, lower and upper bounds on beam height. We can plot our objective function contours on our design space, and we can see what the result is. So at the smaller cross-section dimensions, we have the smaller volume, and at the larger cross-section dimensions, we have a larger volume. So that's what we expect. So, but going to also need to look at our constraints. So we'll do these one by one. Our first constraint is the stress constraint due to the first loading condition, which we calculated previously. We have a function in terms of known quantities and design variables. We know we want this to be less than 200 megapascals. So we can rearrange that equation to put H independently. And then we have H in terms of B, essentially, and known quantities. And then we can assume our known values of B that range across our design space and plot the curve. So this is the curve that we derived by hand. And values of H above the curve are at and above the curve satisfy this constraint, and values in the shaded region are violating our constraint. So the stress in that region of the design space is higher than this allowable. And so that's what we call the infeasible region. So we need to consider the rest of our constraints. We have the stress constraint for the other load case, putting the load in the horizontal direction. That's completely enveloped by the stress constraint for the first case. So that's this smaller region here. We did the same thing, rearrange for H and then assume values for B. For the displacement constraints, we have the equation we derived. We rearrange for H, assume values for B, draw our curve, and we see in this case we've reduced our feasible region by applying this constraint. We have this sliver of a region here where this is no longer feasible because values of H above this curve are the only ones that are feasible. So below the curve, we've increased the size of our infeasible region because these values in this sliver are violating this constraint. The displacement is larger than this allowable value. And lastly, for the second load case, the displacement constraint, we draw the curve, same approach, and we see we've increased the size of the infeasible region because this value here is below our curve, and so these this region designs in this region have a displacement larger than the allowable. So that's all four of our constraints. We see, finally what we have. This is our feasible design space. Every design in this region satisfies our constraints, and so our objective is to minimize the volume that satisfies all our constraints. And so we can look at this contours, and we can see exactly where that point is. We see as we move down towards this corner of our design space that we are minimizing our volume, and as we follow our constraints, we can see pretty clearly that the minimum volume that satisfies all of our constraints is going to be at this point where the this displacement constraint from loading condition B intercepts the stress constraint from the stress constraint from loading condition A, and that's going to be our optimum value. So you can see it graphically. You can just look on the axes what the design is. You can also algebraically solve these two equations and determine that result. So that's the optimum point. So now we can see our design space, we can understand our constraints, and understand our objective function and see the optimum. So this is really what I wanted to provide for people that are brand new to optimization. You can really conceptualize the problem with the graphical solution for these cases where you only have two design variables. So we'll move on to Nastran. We'll solve this exact same problem. And hopefully that gives you the connection that you may not have had if we hadn't gone through these steps of doing the hand calculations and visualizing our design space this way. So I'm going to open up Femap. And I'm going to keep this slide open so I can reference it. So again, I'm going to do this really quickly from scratch. I'm assuming you have some Femap background so that when I create the model, it's not going to be too fast for you to follow, and you can always go back and review later. But the first thing I'm going to do here is I'm going to create the properties and materials I need for this model. I'm going to specify this is a 200 gigapascal elastic modulus. and 0.3 Poisson's ratio. So I just created a material. And I'm not going to do as I normally would and give everything nice names that are that would help for a larger model, but I'm just trying to do this quickly. I'm going to create a beam property typical way. Now, one thing I want you to know about is if you're optimizing beams, the shape option is useful, and particularly you want to pick the Nastran shape option. See this toggle button here, because the way this works is this writes a p-beam L or p-bar L entry that has dimensions on it rather than beam properties like a more general beam where you have moments of inertia and areas, because this is more convenient because the user, get to specify the dimensions, and then you can link design variables to those dimensions rather than having to link the beam properties to your design variables. This is much more convenient if you're optimizing beam cross sections. Pick the Nastran option. So I'm going to start in the feasible region here. So my first dimension is going to be the base. So I'm going to pick something like 4 centimeters, and then maybe 25 centimeters on the other dimension. And you can draw the section, and Femap will calculate these values, although these aren't the values for beam properties that'll be used. What'll be output are the dimensions, and Nastran will calculate these properties separately. I have to pick the material that was created. Okay, so I've got my material, my property. I'm going to create the nodes I need. So I'll put one at the origin, and then I'm going to put a second node at 5 meters. I've got my nodes. This is a really simple model. Create my elements, so I connect my 2 nodes. I'm going to orient my beam axis in the y direction. Pick my property. Okay, so this is my beam element, and I'm going to apply my loads. So load case A, I can create a nodal load, and this is going to be negative 5,000 newtons in Y. So you can compare, that's loading condition 1 here. Load B, I'm going to make it the same node, but this is going to be 100 newtons negative Z. There. Okay. And a constraint. So these are my 2 loads and my constraint. Now, one element's going to be sufficient for these specific boundary conditions. In general, you might need to refine this mesh, or if you're looking at dynamics problems or buckling problems, you might need to refine the mesh. Or a static problem with different boundary conditions, you might need to refine the mesh. So if you're ever in doubt, you can do a mesh convergence study. One element is good enough for these specific boundary conditions for this static case. So I'm going to save this. Okay, so now we've got our finite element model. Now I'm going to just show you some of the new features in Femap for optimization. They're listed under model. Optimization is where you want to start setting up your optimization model. You've got these 3 controls, which are variables and topology regions, limits, manufacturing constraints, and then update from punch. So I'll start with update from punch. Is really convenient. It will automatically update your Femap model from a Nastran solution. So Nastran will write a punch file to have all the final design variable values, and then Femap can read that and update your model for you. It's a lot more convenient than manually going through and updating your model. Variables and topology regions, these are how you define design variables. Limits are how you define responses and constraints. And manufacturing constraints is how you specify manufacturing constraints that are specific to topology optimization. And then the case control type inputs are defined separately in the analysis manager, which we'll show. So this is the variable and topology region manager. So we'll create a new variable and topology region. So there's types that you have access to. You can specify property, material, and element relationships, which creates the design variables and relationships you need for those types. And then topology is a topology optimization specific type where you specify which elements are going to be included in the topology optimization. So in this case, we're going to optimize our beam cross sections, which is going to be a property type. So I'll name this B, because it's I'm going to make this be the design variable corresponding to the cross-section width. We have a property there. So there's different options here that allow you to control types, but this is well supported here. So it's a P-beam L entry, and then for the type of cross-section that we're working with, we have 2 dimensions. So I can pick dimension 1, which is going to be this base dimension. And that's going to create the design variable, and I can specify my bounds. And for this design variable, it's going to be 1 centimeter to 5 centimeters in this values section. So that's what we need for our design variable B, and we'll create a second design variable, which is going to be dimension 2. That's design variable H. And we have different bounds here, 1 centimeter to 30 centimeters. And this window, we have a table summarizing all our relations. So this looks good. We'll activate those when we set up the analysis case. So the next thing we want to do, we did variables and topology regions. Let's look at limits. This is going to be how we define our responses and our constraints. So optimization response, we can specify our Femap UI can specify all the ones listed here. We're looking at 2 types for this problem, which is going to be a stress constraint and a displacement constraint. So we'll start with the stress constraint. And we pick our output quantity corresponding to the Femap categories here. And what we want to do is look at beam maximum combined stress at end A. So that tells us what the response is, and we can specify our bounds. So let's specify minus 200 megapascals to 200 megapascals. Oh, and we do have to select where that's going to be applied. So there, you can do that by property or by element. We'll do it by element. And that should be everything. Okay, and we need additional constraints for the displacement. So let's create those. And we'll create separate ones for our 2 subcases. So we can pick nodal displacement. You can pick whatever component you want. For the first subcase, we want to limit the y direction displacement. So we've picked that. We picked the tip node. And then the bounds, it's 10 centimeters. Okay. And we'll create the last one. So this is going to be displacement in the z direction. We pick that direction. We pick the node again. And the limits are the same. Plus and minus 10 centimeters. So that's our last constraint. So we have a nice tabular view we can review. Okay, the naming's a little bit weird. This is load case A instead of load case A and load case B. I specified the direction on that one. That's okay. It's just a label. So that's the constraints. And we don't have any manufacturing constraints in this case. It's a topology optimization constraint, and this is not a topology optimization. So let's create our analysis case. This may be a little bit different. Normally, if you're not typically doing optimization, you may be specifying statics or normal modes, or picking whatever you need from this menu under analysis type. In this case, picking design, topology optimization. I'm going to use the linked solver to pull from the right license pool. That's dependent on your license setup, so you can ask us if you have any questions about your license setup. So I'm going to create that case, and I have an analysis set tree. It's defining my analysis case. This is going to look pretty typical to what you normally would see here if you're a Femap user, but there's a special option under analysis set options for design and topology optimization. So here we can pick the optimization options, design or topology. We can pick static, normal modes, or frequency harmonic for design optimization. Our goal here is going to be, we're going to minimize volume. I'm going to leave this. You can control the maximum number of design cycles and the output interval. I'm going to leave the defaults for that, but we need to pick our design variables. So we already created these. It pulls up this menu, B and H. And so we picked those, and this menu looks like it's ready. And the next thing we want to do is we're going to have multiple subcases, and we handle that as we normally would with Femap. The way I normally do that is I click on this subcases defined, and I click on multi-set. And for cases where I only have one constraint set, I deselect these, and I apply default constraint set. And I also uncheck this, so it keeps the default constraint that's likely already there. I'll double check that, and then the two load sets. So it creates two load cases that correspond to load A and load B. You can see in the boundary conditions that load A is there, load B, and then under master requests and conditions, I'm going to check that that constraint is applied at the root, and it is. So the last thing we want to do, we defined our loads and boundary conditions, our analysis cases, and our objective function. We need to define our constraints. We're going to do that at the subcase level. So under subcase A, I'm going to click on optimization limits. And here I'm going to pick my stress constraint and my displacement A constraint. So this is this load case where the load is being applied in the Y direction. I want to limit the response in that direction. And then for load case B, I'm going to pick optimization limits again. And I'm going to apply the stress constraint, and I'm going to apply the displacement constraint in the other direction. So that should be all I need to do to solve this problem in Nastran. Let's preview the file. I'm not going to review this file right now, but typically I would review this. I would check the different subcases are set up correctly. So I do see that I have two subcases. I have an objective function defined. I'm not going to review these inputs, but I would typically kind of spot check these inputs versus the Nastran formatting. But let's just let's run the case. So I've activated the analysis case, and then I'm going to hit this Analyze Model button. Okay, it finished. The first thing I typically do is look at the FO6 file, these optimization cases, and I usually start at the bottom of this one. There can be a lot of output sometimes. Let me zoom in on that. So at the bottom, you have the summary of design cycle histories. You have a table of results where it compares the objective function histories and the constraint value histories and the history of the design variable values. And there's a comment about the convergence. So run terminated due to hard convergence at optimum at design cycle 6. So that's what you want to see if things are going well. And you want to review your tables. One thing Femap can do for you is it will actually read this data into functions, and you can plot your tables. It's a little bit easier to interpret the information in chart format. So that's the same information as is in this table. And qualitatively, you're looking to see if things are converging and stabilizing. That's a positive indication. It's not a guarantee of a global optimum, but it's something that I like to check. So you can chart the different quantities. There's also the constraint value history in the table. So Femap will plot that for you. So the way I'm doing that is I'm selecting these functions in the model. These were read after the run from the output. And so I right click on that and I say show in charting. And so everything's looking like it's at least the optimizer is settling on a design there. So that's sort of a secondary check. And there's different things that, for problems that are having trouble converging, you can get a better sense of what's going on by plotting the history. So Femap allows you to do that. And then the last thing, so let's check and compare this result to our to what we got from the graphical solution using hand calculations. So the objective function, this is the final value of the objective, the optimum volume. So we got 2.13 e to the minus 2. So we reproduced our result. So the objective function, which is volume, is matching our result from our hand calculation and graphical solution. And then our design variables, we have 2.42 e to the minus 2 and 1.76 e to the minus 1. And we see that they're matching. So that's kind of nice to see that we can solve a simple problem and have this level of conceptual understanding of design space and then reproduce the result in Nastran. So that's what was just done. So that hopefully helps you develop your understanding and get started in here. Now, this is a pretty simple problem. The power of Nastran is to be able to apply this to larger problems. You probably have fairly large models in Nastran that you want to optimize that have more than one element. And that's what this is for. So with Nastran, you can expand to much larger models, many design variables, analysis types, and apply the same concepts to that. So the next example, I think I can get through quickly, and then maybe we'll pause for questions. We're gonna look at a slightly different case of topology optimization. So this problem is taken from this paper by Sigmund, 99 Topology Optimization Code. It's this figure 2 example. And there's MATLAB code that you can look up online that comes from this paper, and you can play around with that, but we're not going to get into that here. But what topology optimization allows you to do is take a domain where you don't know the topology of the structure, but in this case you have a cantilever structure, you have some load you want to support here, and you have some area, some region where you can put material to support that load, but you don't know what topology that you want to explore with using an optimizer, what the efficient topologies are in this space. And that's what topology optimization allows you to do is using a mesh that fills this domain. The optimizer will pick where the material is to satisfy the optimization criteria, which typically is for a case like this where you have a static case. The efficient approach typically is to minimize compliance, which is proportional to strain energy of the entire structure, and then you apply a constraint to the mass of the structure to achieve some volume fraction to cut out some of this material. And we don't have too much time to get into different approaches, but that's the approach that I would start with is minimize compliance and apply a volume constraint and handle it with that approach. So let's set this up really quickly. I'm going to create a surface here. I'll create this from scratch. You can follow along. It's only going to take a second. So I'm going to create just a surface to reproduce this domain. So that looks consistent. And this is sort of a non-dimensional example in the paper. So some of the physical aspects are less important for that type of academic problem. Obviously, in a real-world situation, you're going to use the materials that make sense. But here, I'm just going to load a material. So I've created a material. I'm going to create a property. I'm going to use a plane strain property and give it unit dimension and thickness. Apply my steel. Okay. And I'm going to use the meshing toolbox to mesh this. So go to mesh surface, map to mesh. I'm going to pick that property that was created, and then I'm going to pick a unit mesh size. So that created my mesh. I'm going to create a load to match. I'll do it at a point this time. This has associated geometry. So I'm going to create a load at that end to match this image here. Let's say minus 1,000. And a constraint. I'm going to put it on the geometry again. Fixed. So I can kind of turn that off. You can see the original domain with the boundary condition and the load applied on the geometry, which is associated with this mesh. And let me save this. So we have our mesh. For topology optimization, we're going to go to the same options we had: variables and topology regions, limits, manufacturing constraints. We'll start with this variables and topology regions. We'll create a new region. That's okay. This I have to pick topology optimization here under property. The type of element that I'm using is not allowed, but for topology optimization, it is. So this allows me to create the region where I tell Nastran which elements do I want to add and remove material from. And so it's pretty intuitive. You pick the ones you want. Here, I'm going to pick most of them. I'm going to leave a row along the bottom here to keep those elements. But you can see, you can highlight the ones that are selected there. And then there's active and frozen options. You can pick which ones are not being optimized instead of the ones that are being optimized. Here we're picking the active ones. It's gonna optimize those elements. So that's been created. Optimization. So for limits, I'm going to create a limit here. For this example, what was used was a volume fraction of 0.4. So what the optimizer had to remove material until the volume was at 0.4, the original volume. So I'm going to do something similar here. I'm going to use a weight constraint instead of a volume constraint. And then I'm going to set an upper bound on weight. And I'm just going to pick 0.4. So conveniently, this pre-filled value is actually the weight of the mesh calculated using that weight check tool. So it defaults to that in Femap. But if you need to check that, you can use the tools. You can use the weight check tool to check that. So I'll do that really quickly. But the upper bound, I can use math operators in these fields. So 0.4 times that value is going to be what I want to sort of match the volume fraction that was specified by Sigmund to follow this example problem. So I have an upper bound there. Just to show you how to check that that mass, you can go to Tools, Mass Properties, Mesh Properties, select all, and then we see that 0.469 value is listed. So it defaulted to that in that field. Okay, so we've set our topology region, one of our limits. I'm going to add a manufacturing constraint. In this case, so we don't have time to go into too much detail into these manufacturing constraint specifics, but one thing to be aware of, checkerboard constraint is something that is on by default, something that you want on by default. So we don't really have time to get into it more than that, but that's something to be aware of. I'm going to put a minimum member size constraint on this. I'm going to set that to 4. So that's what I wanted. So let's see. We've defined topology regions, limits, and manufacturing constraints. So let's set up our analysis case. This is going to be similar to last time. We'll set up a new case. Design topology optimization again. Under options, we go to the same menu, design topology optimization. And this time under type, we pick topology. The goal, we're going to pick compliance. That's what we talked about previously. It's consistent with this problem, and it's proportional to strain energy. I'm going to put like 100 cycles here. That's just the maximum number of design cycles. I can pick topology regions. So this is the region that we set up. You can use these toggle buttons to see the active and inactive regions. So the green are going to be optimized, and we can select our manufacturing constraint here. Okay. And then the last thing we want to do is our mass constraint, which is going to be related to our volume constraint for this example. So that's going to be under master requests and conditions, optimization limits, and our mass constraint. Okay. So I'm going to save this, and we'll get this started. And I think we're just at 2 o'clock here. This is a warning. I don't think that's going to be an issue for us. It seems to be working. This is related to licensing. So this is going to run for just another minute. I think after this, we'll stop and take some questions, and then depending on how that goes, we can decide if we want to cover the last problem or not, or maybe make a follow-up video that people can optionally watch on that. Okay, so it finished. Under results, I can see my last design cycle. Now, one output quantity that's going to be interesting to look at is this normalized mass density. That's effectively telling us if the material's been retained or not. So let's look at criteria view here. And we'll look at, turn off these labels. And we'll set up limits to capture a maximum here. So I just, quickly use criteria to turn off elements that had a normalized mass ratio less than 0.8. So that's sort of the design variable range. So from 0 to 1, and 0 means that the element's been removed, and then near 1 means you retain the element. This is Nastran solution for this topology optimization problem, which is indicating a topology that's going to be efficient with the volume fraction that we have for this loading condition. So that's a semi-new feature. Starting with NX Nastran 12, they made it pretty easy to set up, I think, and then you've seen this problem from scratch. It's a simpler problem, but it allowed us to do it in the allowed time here. So there's some other examples online that I won't go into now, but if you go to our website, we have a case study where topology optimization was applied to this transporter ejector launcher. You can do topology optimization with solid elements and more complicated models if you need to help you with your designs. So for that, I think we should stop for questions now and see if we have any questions and then go from there. So Jonathan, I don't know if you want to take it back.
Yeah, thanks, Anthony. So I have a couple questions that have come through the chat. Feel free to keep sending those in. I think I'd like to go through those questions now and then push on with the wing example, if that sounds good to everyone. But I can go through some of those chat questions. And I guess just kind of to start off, how does solution time for solution 200 compare to, if you're doing an optimization over a static run or a modes run, how does that compare to the normal solve time for one of those runs?
So it depends a lot on the number of sensitivity calculations that are required, which are going to be dependent on the number of constraints and design variables. So it's hard to answer that question. I would say it's maybe one order of magnitude longer, but it's going to be case dependent because of the sensitivity calculations being expensive, and those are going to be dependent on the specifics of number of design variables and number of constraints. And if you have a large number of either one of those, then it requires a lot of work to calculate the sensitivities, and that's going to drive up the solution time proportional to that.
Okay, awesome. Next question is related to artificial stresses that you get at rigid elements or boundary conditions, things like that. If you're optimizing over stress, is there a way to keep it from picking those up?
Yes, you can leave them out of the group. So you have control over what elements are being included in the constraint. If you have specific elements where there's a singularity in that group, you leave those elements out if you don't want them included. So I can show real quick awesome. That, but it's as easy as making a group. But when you specify that stress constraint, let me just see if I open that model back up. Example 1, under the limits here, we had a stress constraint. So I'm just going to edit that. And under entities, you can pick where you want it applied. And so here, I only had one element, but this is the normal dialog box. So you can pick and choose what you want the constraint applied to that way.
Okay, great. Yeah, so you could just use that to choose your one element away if you wanted to.
Yeah, exactly.
Awesome. Next question. Do you know if optimization of shell element thickness would work with 2D laminate elements? And would that let you look at layups and ply thickness and material orientation? Do you know if that's supported?
So it's, what is supported? So yes, but the design variables need to be continuous. And so things like individual ply thickness and ply orientation, you can use the optimizer directly as shown in these examples to optimize those quantities. But if you're looking to optimize number of plies, then you may have to implement something differently, either picking and branching your design and fixing the number of plies and then optimizing separately the different configurations and treating it like a trade study where you're comparing two different things. So you can work around that, but the direct support with the gradient-based optimizer internal is going to be limited to the quantities on those laminates that are continuous.
Okay. And then I think the final question for now. Sorry, I'm looking through the chat at the questions I have. If you're doing the weight limit in the optimization, is that based on weight or mass? And does that change based on the value of the weight mass parameter? Do you know?
Yeah, that's sort of a Femap-ism, a Nastran-ism. So in Femap, it shows it as weight, but if for a model where weight's really not defined, like none of the models I actually showed here, I defined weight mass parameter, and so in that case, it's mass. So you do kind of have to look at the output from Femap if you want to confirm things like that, because the Femap interface, they chose to label it as weight, and it could be weight in situations where you're using weight mass, but you would have to double check that in what gets written out of Femap to make sure you understand what it's writing in terms of that response, what the quantity is. I would be double checking that if you're running into that situation. But the ones today, it said weight, but it was mass.
Okay. Yeah, and that sort of goes back to I think one of our last webinars was on the weight check command and weight versus mass and what you're seeing and how to review the Nastran files that come out of that. So I think my final question before I think we can kind of jump back into the final wing example. Is just kind of at a top level, these are inherently Nastran capabilities that you are able to set up pre-processing and even some post-processing using Femap. How do the capabilities compare for NX or Simcenter 3D to set up these optimization Nastran problems?
They are similar. There's some nuances where they'll be different, but in general, Simcenter 3D is going to offer similar capabilities. One thing you might notice is Femap, yeah, the types of design variables and the types of responses are generally similar, and there may be some differences. There's a specific difference in that Femap chose kind of a more convenient approach to the user with less control, where in Femap, you don't actually specify the design variable. It sort of has a workflow where both the design variable and the design model relationship is set up at the same time, and you can't control how that's set up as much, but it's faster to set up. In NX or Simcenter 3D, they added essentially a step where you can set up the design variable and the design variable to model relationship in 2 steps, which takes longer, but it does give you more control in situations where you might want that. And in terms of the specific responses and analysis types, there may be some differences. I would have to review NX specifically to know if there's native support, maybe for a few different more analysis types. But NX does have NX and Simcenter 3D. They have native support for topology optimization as well. And overall, I would say it's generally similar level of capability.
Perfect, thank you. So I think that's all the questions that I've received in the chat so far. So if everyone's up for it, I'd be interested to see the wing example.
Okay, can go for it. Yeah, and I understand this is going a little bit long, so you know, if you have time and interest, then you know, I'll go ahead and go on to the next example. But
and I guess while you're setting that up, kind of the final note that I'll share is all of this is included on a recording. So if you need to jump off now for another call or a coffee break or whatever, you can certainly come back and catch this final example on the recording as well as the question and answer session that we just finished and the one at the end will all be included on the recording. So awesome. Thanks, everyone.
Yeah. Okay. So I'll go through this. I'll try to be quick on this last problem, and this will not be done from scratch. So I have some reference models, and we can just sort of look through those and get some interesting things out of that. But it's an aircraft wing model, 70,000 pound aircraft, which influences the loading on the wing. We have a wingspan and some wing parameters there. We want to minimize the weight of this wing. We have 26 design variables, which are including wing skins, spars, rib thicknesses, and stress constraints for 4.4 G maneuver load, and then a modal frequency constraint of 8 Hertz. And that's to simplify dynamic problems, eliminate potential dynamic problems. We just have that constraint there. So this is the wing model. I have a load applied, a load case applied that corresponds to the 4.4 G maneuver load, sort of applied at certain ribs where the distribution is localized to approximate the wing aerodynamic load. So I'm just looking through this model now. We have a constraint at the root and loads applied. I want to look at the initial thickness values, which I think is displayed right now. So if you want to do that, actually, I moved this icon up, but I think if you hit the toolbar options, in this menu, you should be able to get this model data contour. Maybe it's on by default. I have some custom settings in mind, but you can turn on these model contour data. So I just turned it off, but you can toggle it on and off that way. And what this is showing is the initial thickness of all these skins, spars, and ribs are at 1/2 inch. You can see the different bays here. I'm just turning transparency on and off. You know, we have spars running along the forward and aft components of this wing, and then we have skins along the top and bottom and ribs. So the design variables have been set up already. Under model optimization, variables and topology regions. Independent design variables got set up for the ribs. The skins, top and bottom, are linked together, and then the spars. So let me see if I can show selected. Yeah, it'll highlight those. So we can sort of toggle through those. You know, this design variable is corresponding to this rib thickness. You know, and you just go along the span. There's independent design variables that are and regions that are corresponding to the different ribs. The skin, you know, top and bottom. There's one design variable controlling that. So there's span-wise variation allowed. So there's sort of discrete values for these panels, and design variables are gonna adjust these thicknesses to achieve our design. So there's quite a few set up there. So I think there's 26 total. You know, we've seen the process for setting these up. I'll go ahead and edit selected so you can just be reminded. Here we picked up property again. You can pick, so here we have multiple properties. Pick the one you want, pick the field that you want on the property entry, and then the limits. if you have bound constraints on that design variable property relationship. So that's the design variables and the bounds on that. You can see in the table we just had open. For limits, what we are constraining here are stresses. Now, if you remember from the presentation, we're limiting the von Mises stress 30 KSI. And so we have separate constraints set up for the top and bottom of each element, and then also the frequency constraint. So top von Mises, bottom von Mises. Let's just open that up so you can see here. It's picked the response quantity, it's applied. You can see where it's applied to all the elements, and then picked an extremely low, lower bound. It's just a numerical choice. You could have put 0 there, but I didn't. I just wanted it to not be near the constraint if there were some elements with low stress. So 30 KSI upper bound, and then the modal frequency constraint. You can pick under category frequency, pick the eigenvalue number, and then you can pick the bounds on that. So I think that was everything. In this case, we have, these manufacturing constraints are topology optimization specific. This is not a topology optimization problem. We've got constraints, we've got design variables. So let's go to our optimization analysis case. Well, why don't we just go ahead and run this real quick and see the results that we're starting with. That's something I like to do. Since we're sort of on overtime here, I'm just going to start with that. So I have a static analysis case set up. It's just that same loading condition, same constraint, and it runs fairly quickly. I mean, this is for as much as is in this model, it's still fairly quick to run. So I just ran that static case, and I want to look at our results to see our starting point. So what we see here, these are stress results. Let me double check my view here. So it's von Mises stress. I have double-sided planar check. So it's showing top and bottom von Mises stress on the same results. And what I see here is I have 91 KSI. So I'm horribly violating my constraint around this corner. And if you remember my initial design, I have uniform thickness here, and so it's not thick enough here in terms of the skin thickness at least, and it's overkill near the tip. So what I want here is for my optimizer to taper this wing a little bit so that I have material where I need it. And right now you see we have issues here, and we have potential to decrease the weight of this wing based on, at least from a stress standpoint, based on this result. I'm going to run modes really quickly also. Same boundary constraint here for the mode solution. And I see I have a 3.5 hertz mode, which is violating my constraint. So I want at least 8 hertz. So that's where we're starting. Let's go ahead and set up this this optimization case. So I don't have this all set up yet. I'm gonna have to go through and review. So here, this is a design optimization problem. I'm gonna pick none because I'm gonna pick subcase specific analysis types because I'm gonna have a statics case and a modes case. I'm gonna minimize weight. And I've already selected the design variables. So it's all 26 of the design variables that were created. So this is what I need it to be. But we still need subcases defined here. So let me create my first subcase. And here you can pick the different types. So normally this is at the analysis level. Here it's under the analysis case, the subcase level, so I can pick static. And here it's putting me right into the optimization limits menu. Now for this, I only want my stress constraints to be active. The modal frequency constraint doesn't make sense for this static case. So I'm going to pick those two stress constraints. And if I hit new there, it's kind of maybe less intuitive than some other things. But if you select a case and hit new, it'll allow you to make a new case. So my second case is going to be a different analysis type. It's going to be in the same run, but I can pick normal mode's eigenvalue. And for this case, I'm going to pick my modal frequency constraint. The stress constraints don't really make sense to have active for my mode solution. So I have my two cases. And I want to double check my load is correct here for my loads and boundary, my overall boundary conditions, which is my loads and constraints. So that's not actually set up. So I need to go in here. I need to pick my constraint. So I fix the root. And then in this case, I want that 4.4G load, which is this load case for my static case. So that's now been created. And then I also need the constraint applied for my mode solution. Okay. I think something's not right here. This should be active. Under optimization limits. Let me just double check my constraints. Those two are set. Those two are set. I may have set it under the wrong menu. That's this master case, I think wasn't set up correctly. This is sort of the default for the two subcases. If you leave this blank, then it goes with the subcase. It's typical Nastran stuff where if you specify something above this subcase level, that's the default. So you just want to get that right. Let's preview the input. So we got our objective function defined that's corresponding to weight or mass. We should have two constraints sets here. Boundary conditions and loads look good. Okay, let's try this. There's a lot that goes into this, and we'll see if I got everything. But generally, those are the menus you want to review. Hopefully I got everything right. So this might take a couple minutes to solve. It's going pretty quickly. So it's capped at 100 iterations. It's already at 7, so it's not going to be that long.
So I guess while this is solving, what would the workflow look like if you wanted to consider a different number of ribs? So for instance, this has 8 ribs, I think. If you wanted to look at 7 or 9, what would that workflow look like?
So that, you can't make, so topology optimization is the only way you can have the optimizer add or remove elements. So you would have to set up, so if you didn't want to use a topology optimizer to optimize the rib topology, which would allow it to remove the rib, you would just make 2 models. So it would be 2 configurations where you just ran with separate number of ribs in that case. So you have to make separate meshes and handle it that way. I mean, it depends if you're saying you needed to shift the rib location in addition to adding and removing the rib. So if say you just wanted to morph this entire mesh for the same number of ribs, you could set up a shape design problem and handle it that way. That there's not direct Femap support for that, but that's something you could do with some manual work. Let me review this. So it's about halfway done. I don't know. I guess while that's running, we can open it up to any additional questions. If you got any more, Jonathan, or if anybody else wants to jump in and ask.
Yeah, I think my other one for now from the chat is just kind of clarifying that you have body loads in this case, but this could work with acceleration loads, or like there's not really a limitation on the type of load you put in the model, right?
No, there's generally not. You do want to be careful with topology optimization on the certain types of loads, because the nature of that type of problem, if you specify a load, like a body load that applies to the entire mesh, the optimizer's going to have a hard time removing elements because you have load applied everywhere. But for design optimization, that there should be no problem, like a gravity load or some other type of body load. I'm not aware of any limitations on that generally. In this case, I don't have the gravity load applied, so this is, yeah, typically on a maneuver load, you may take advantage of the inertia relief effect and use that to your advantage. I haven't done that here. The wing is pretty light comparatively, so that was sort of, since I'm also, assuming there's a fairly heavy aircraft attached to this, the inertia relief effect is maybe not as important as it may have been otherwise. So this finished up. So let's do two things. We'll look at the final design cycle here. The modes results don't seem to come through from the optimization output case. I don't know if that's maybe Femap skips that portion of the output. So we'll look at that in a second, but we don't have that yet. Let's look at our result here. So this is the static result for the final design cycle. And what we have here is the stress distribution for that result. And what you'll notice is, I mean, we don't have really the constraint active is what I'm seeing here. So this is 25 KSI. We were allowed up to 30 KSI. And I don't see, it would show up in the contour if we had an element with stress distribution higher than that. So that constraint does not appear to be active, meaning it's not driving the design. So we're going to want to check that modal frequency constraint and make sure that's active to make sure that we have a result that makes sense. Because one of the two really needs to be active. Otherwise, that we should have additional option to reduce the weight if we're not at a constraint or not at a bounds. The other thing that I like to do here is let's, well, yeah, I'll show you. I was about to show the element thickness. So this is the element thickness of the model we have in Femap right now. Now that result we were just looking at is the result from the optimized model. But the actual model hasn't been updated yet. So this thickness values are not in our Femap model yet. So the really great thing that we can do is use this optimization update from punch. And that's going to update our model automatically. So this is the OptWing model. We have a punch file. So we can open that up. And that updated all our properties. There we go. So now we see this modified thickness where we have distributed, we see the taper that we expect for this type of wing. And so the optimizer has added material and has tapered the wing down to, this is the lower bound. So we didn't allow the optimizer to reduce the material beyond this, but we see, about from midspan, we have a tapered wing by this contour. So now that we've updated the model, let's just rerun modes. And I want to make sure that that modal frequency constraint is active. So it is. So if you remember, that was an 8 Hertz modal frequency constraint, and we're about 8 Hertz and some tolerance that Nastran used there. Oh, and I need to turn this thickness off to see the displacement result. So that's our first mode. So all that material got added to drive this frequency up to 8 Hertz. So that's the only active constraint. If we wanted to, we could remove that constraint, and then we we'd see a different design where we should see active stress constraint in that case. So I'll start a run without that, and then we'll see if there's more questions, and then we can see the result from that. Since the way I'm going to handle that is I'm just going to delete this second case, which is the modes case. And we'll run it again. Oh, and the other thing is, normally we would check convergence. I didn't open the FO6 and do what I normally would in this case, but we have the same information that we talked about for the beam problem, where we can look at the design objective history, and we see we actually had to increase the weight of this wing to satisfy those constraints for that first run. There's some noise here, so we probably could have done something to adjust the convergence criteria to maybe not have it run so long, because of this noise is causing the convergence criteria to fail. So this is one of those examples where you can start to pay attention to the convergence history and maybe make some adjustments. I might just kill it, run it once and see what happens, and then you see it's kind of converging in 30. So if you want to, if you know what you're doing, you can play around with different parameters and get the most out of your solves. Because we see it's pretty much in a stabilized region here. Now, if you're a grad student and you have a committee, they're going to be asking you about necessary and sufficient criteria for local optima, and you're going to have to do a little bit more work and make a better case. But if you're working in for your manager, your customer, and they're going to be looking at the design outcome, and so you can kind of use a looser check on convergence and maybe get away with it in certain situations. So it looked like that second run finished. So let's check that. That ran fairly quickly. So we have design cycle 8. So, and here what we see is, since we didn't have that modal frequency constraint, we know the stress constraint needs to be active, because that's the only thing that's keeping the optimizer from removing material, and it is. So we have 30 KSI and some tolerance. We see it's optimized each bay to sort of have at least in the top skins we're hitting maximum allowable stress. So it's this is sort of what you'd expect. So, this is maybe a more intuitive result than the previous result, where really the material design was being dominated by that frequency constraint. It was adding material to stiffen up the wing. And in this case, that constraint's not there. And so this is the active constraint. And this should be a lighter design than the previous design. So maybe this is like a trade-off you could do if maybe that 8 hertz is just sort of arbitrary and you're trying to avoid dynamic problems or controls problems, and maybe it's worth dealing with if you can save a lot of weight. And we can see the difference here. So there should be a previous design we can show in charting, and then we should be able to show them at the same time. Actually, if I highlight both. So there's a huge difference actually. So this is around 4,000 pounds versus 7,000 pounds. So we saved like 3,000 pounds by saying, we'll take the frequency that we get and deal with it on the control side or something else. So that's a trade-off type scenario that you might find yourself in. Okay, so I'll stop here. I guess if there's any final questions, you can hit those, but we've already had.
So thank you, Anthony, for the great detailed presentation. I know I learned a lot. I hope everyone else did. I appreciate everyone sticking around for our extended presentation today. I don't have any more questions in the chat. So if you have any final questions, I'd invite you to put those in the chat now. You can also unmute yourself if you'd like to speak up with a question. But otherwise, like I mentioned previously, we were recording this entire presentation. So if you want to go back and watch any of it again, try any of the examples on your own, you'll be able to do that. And we should have that recording available in the next day or early next week. So keep an eye out for that. I'll send an email out to everyone who registered, just letting you know when that becomes available. But otherwise, if there are no other questions, I think we can wrap up. Thank you again to Anthony and to everyone else.
Yeah, thanks everyone for sticking around. Appreciate you coming, and talk to you soon.